Well, yeah, thanks, Karen, for the introduction, and thank you to all the organizers for the original invitation and the opportunity to give this talk. It certainly it was a very nice workshop, and I'm hoping that this talk will also contribute to that. So, as Karen said, I'll be talking about subsampling and adaptivity in multi-level Monte Carlo for the particular application of efficient risk estimation. And let's see if I can do this. There you go. Right, so this is the outline, but let me just jump right through. So the just as a motivation, I like to have this one slide about risk analysis and risk assessment. So in stochastic models, it's important to do a lot of calculations and because they are increasingly being adopted in real-life applications. One of the most important applications is, or the most important questions to be answered about these stochastic models is assessing the risk of some extreme event. Here I have some examples, starting with finance, which I'll be focusing on the rest of this talk, but also there are other applications in industrial modeling and crowd modeling, or even in workshop organization as we are learning here. And to assess the risk is the first step in risk management, and to do that, we usually compute risk measures. Let me just, right. And computing risk measures is computationally difficult. And here I'm trying to summarize the reasons why that's the case. So first of all, they are rare because they depend on these catastrophic events. And second of all, that these risk measures are not smooth. And that's because they depend on the fact that either the catastrophic event has happened or not. So that corresponds to, in the usual case, a discontinuous function if you don't apply any smoothness or any smoothing. And finally, the underlying stochastic models that are involved are usually difficult to evaluate, or in our case, expensive to approximate. So in this talk, I'll be addressing these last 2 points, mainly that the risk measures are not smooth and the underlying stochastic models are difficult to evaluate. The events I'll be talking about are not extremely rare, they are just rare. And for extreme rare events, usually importance sampling is used or other methods are used to bring down the event from extremely rare to just rare. And then the topics in this talk will be more relevant. Right. Okay, so as I said, I'll be focusing on financial portfolios, financial application. So in this case, I'll model my loss as I'll model losses from multiple components in the system. In a financial setting, that would be options in the system. So I have P random variables that are modeling the loss coming from P different components or P different options in the system. And the losses are depending on another random variable, Y, which is the underlying risk factor. So in finance, that would be the prices of the assets. Okay, so the price of the assets affect how much I'm losing in each one of my P options. And then what's interesting here is the expected loss. So the expected loss is the expected or the expected average loss. So it's the expected value of this average of all the losses coming from the P components or P options, given a particular risk factor, particular value for the risk factor, which I'll be referring to as risk scenario from now on. Okay, and now we are interested in computing the probability eta of exceeding a certain threshold of the loss. So if we have lambda eta to be this threshold, I'm interested in computing the probability that my loss, which is a random variable because my risk factor is a random variable. So I'm interested in computing the probability that my loss is greater than that threshold. And that's a very important risk measure because it tells me what's the probability that I'm going to be losing a lot of money, for example. So I can write that as an expected value of a Heaviside function of another expected value. So the expected value inside is because lambda here is defined here. And so this is the inner expectation, and then this is the outer expectation. The outer expectation is with respect to the risk factor, and the inner expectation is with respect to the loss random variables. And the Heaviside is the problematic part here that I was talking about in the beginning. So the key message from this slide is that the probability of large loss is a nested expectation with a Heaviside in between. So let's focus on that part. Here I'm dropping the threshold. Let's just focus on the loss variables. You can redefine the loss variables to include that threshold if it's fixed, which we assume. Right, so how do I estimate this? I can use a Monte Carlo estimator to estimate the inner expectation, okay? And I'll denote that Monte Carlo estimator by x bar n. So I'm using n samples of the sum to estimate this expectation for a given risk factor or a given risk scenario. There is some weird effect going on here, at least in my slides. So this one leads to a bias of order 1 over n times p. This might be not very clear, but let's take it for now. For granted, I'll explain later a bit more where this is coming from. And then, so this will approximate the inner expectation, which leads again to a bias. And then I have to approximate the outer expectation using m samples now of the risk scenario. Of the risk factor. So we're using m risk scenarios. And this leads to a sampling error now of order 1 over square root of n. So now I have to pick my two approximation parameters, n and m, to achieve a certain error, epsilon. So this is what I do here. And I have to at least have one sample n for every risk factor. So that's why there's a maximum here. And then the cost obviously is the multiplication of all the parameters, m times n times p, because I'm having to sample the inner sum for every risk factor. And so the complexity is just the multiplication of these three parameters, and it's this one here. So what you see here is that, first of all, the complexity increases with p, at least for large enough tolerances. And when this one kicks in, it's epsilon power minus 3, so it's not ideal. What we would like is to have a complexity that is of order epsilon power minus 2, the canonical complexity of Monte Carlo, which is independent of p, does not increase with the number of options, and yeah, as optimal as possible. And to do this, we will do two things. First, we'll divide the strategy to sample the sum that we talked about, such that the complexity does not depend on p, to bring down the complexity to epsilon power minus 3, so we don't have this maximum anymore. And second, we will use multi-level Monte Carlo to bring down the complexity from epsilon power minus 3 to epsilon power minus 2. Okay, so let's do first step now, to where we are estimating now this sum with a cost that does not depend on p. And this actually connects a lot to the previous talk on unbiased multi-level Monte Carlo, because we use the same idea of random subsampling. So here, let's focus just on computing the sum for a particular risk scenario y. So we write this average as 1 over p times an expectation, where now the index j is a random index now, with probability j equal I to be equals pi. So this, by just expanding this expectation, you get back the sum, just like in the previous talk. And then we estimate this expectation using Monte Carlo. Now, the cost of this estimator is exactly n, because we're assuming the same, we're assuming O1 cost for all the xi's. So the cost is exactly in the number of samples, while the MSE is this here, is bounded by the second moment of this estimator. And then we can minimize the this mean square error by picking up the optimal probabilities, which turned out to be proportional to the expected value of xi squared, just like, again, before, the talk before, where we have now the second moment of gi squared, the second moment of xi, which, of course, we don't know these second moments, but we can get some approximations and use those to optimize the probabilities of selecting that particular loss variable, and then plugging this back into the mean square error, we get that the mean square error becomes 1 over n. So we have a cost that is 1 over n, and we have an MSE, or mean square error, that is also 1 over n. So we have a complexity that is independent of p, just like we wanted. Right, so how does that help us in the nested expectation? Well, just as you would expect, you just, instead of using now this sum, we estimate this quantity here. So my variable x now is just the random, I pick a random option, j, and then calculate this quantity to get a random variable x, and then I compute, as before, the expected value of the heavy side of the expected value. where these are the probabilities, the optimal probabilities. The key point here is that these J's, which are again approximations of the expected value of x squared, they should, in theory, to get the optimal complexity, depend on the risk factor y. But of course, if that's the case, then for every risk factor, I have to estimate p of those values, of these G values. So instead, what we suggest is to use some relative weight estimates, for example, depending on the expected value of x squared for all possible options that do not depend on the particular risk scenario. The hope is that the relative importance between the different options does not really depend, overall does not depend on the particular risk scenario, and then our allocation of samples across options should be more or less optimal for all risk scenarios. So this again will allow us to get a complexity that is independent of the number of options. And there's a note here about using a mixed subsampler in which we can use, in some edge cases, we can sample particular options all the time and sample the remaining options. So particular options that are maybe cheap to compute, or they have a big nominal value, we can sample them all the time, and the rest we can sample using random subsampling. So I'm not going to be talking more about this because the case in which this is helpful is very edge case. It's only really helpful when the number of when the variance of these big samples or big options is close to zero. So instead, let's now focus on how to apply multi-level Monte Carlo to the nested expectation to reduce the overall complexity from epsilon power minus 3 to epsilon power minus 2. And this we do in the usual way. So here I have my construction of my multi-level Monte Carlo hierarchy. So the expected value of Q, I write it as an infinite sum of expected corrections, and then I truncate. I do two approximations, truncate the infinite sum into a finite sum to get a biased estimator, and estimate every expectation with an independent Monte Carlo sampler, where the M here is the number of the outer risk scenarios. So here Q is my quantitative interest Q is the heavy side of the expectation, the real expectation. My QL, the approximation, is the heavy side of the Monte Carlo approximation, and the correction is the difference between two approximations, one using NL samples and the other one is using NL minus 1 samples. So the correlation that comes between the two quantities here comes from the fact that I'm using the same risk factor, the same risk scenario, Y. And so I'm relying on the fact that I have the strong law of large numbers to get the correlation. You can increase the correlation a little bit by using the same inner samples in X bar, in this Monte Carlo sampler and this Monte Carlo sampler. And in fact, you can also increase the correlation a little bit by using an antithetic sampler with this, between these inner samples here and the inner samples here. But all of these, they do not change the rate. Whether you use the same samples or you use antithetic sampler, they do not change the rate of convergence. The main convergence of the variance comes from the fact that we are using the same risk factor between the two.
Abdul, a really quick question for you on the last slide from Umberto. He says if the PJ is sum to 1, why do you keep one of the
Sorry, your voice is breaking up, but I can read.
A quick question on the previous slide.
Yeah.
If the PJ is sum to 1, why do you keep one over P in the estimation? Why do you keep P in the
So the PJ is sum to 1, but I have already 1 over P, and I'm approximating the sum by this PJ, but the 1 over P is from there already, from the previous, from this problem setup.
Roberto, does that answer your question? Capital P is the number of risk factors, right?
Right. Capital P is the number of not the number of risk factors, number of options.
Number of options.
Right. So it's the number of options in the portfolio, and I'm estimating the sum with this expectation where the probability is now sum up to 1, but 1 over P is outside. That's why I keep it here. Okay.
Roberto, does that answer your question? Thank you. Thanks.
All right. So then, right. So let me just, I'm going to summarize the multi-level Monte Carlo setup, just because to introduce notation and show that what I talk about later is more understandable. So here is my usual, as I said, multi-level Monte Carlo, where I have the infinite sum truncated and then estimated every expectation with a Monte Carlo approximation. And then we know that if we assume some certain assumptions on the bias, variance, and work, and here I'm just using the standard notation, and that's the whole point of this slide, is just to tell you that I'm interested in the alpha, which is the rate of convergence of the bias, beta, the rate of convergence of the variance, and gamma, the rate of increase in the work. If I know these parameters, then there are optimal choices of the number of levels, L, and the number of samples on every level, ML, such that the complexity is this. So here, the important point is that if beta is greater than gamma, then I get the optimal complexity epsilon power minus 2. And in fact, in that case, the p here is 0 if beta is greater than gamma. If beta is equal to gamma, I get p equal to 2. But the important part is that the important part is here, which is epsilon power minus 2 when beta is equal to gamma or greater or equal to gamma. So compare this to Monte Carlo, where you don't have the minus beta over alpha here, or plus beta over alpha. So now what I will be focusing then on is the alpha, beta, and gamma parameters in my computations. So let's talk about what is this alpha, beta, and gamma. So my Q, again, is the heavy side of the expectation, of the exact expectation, and I'm approximating by the heavy side of the Monte Carlo with NL samples, which I called QL. So if I use NL equals to 2 to the power L, then I get gamma is equal to 1, because I'm increasing, gamma is here is 1, multiplying L. Alpha is 1, and beta is half. So why is that? Let's focus on the particular risk factor or risk scenario, Y1 here. And I'm trying to compute the expected value of X given Y1. So we know that a Monte Carlo approximation is going to be a Gaussian centered around the exact approximation, where the width of the Gaussian is scaled by sigma, the variance of X given Y1, and divided by the square root of NL. So NL again here is 2 to the power L in this particular case. So what is that? So, but then what I'm trying to approximate really is my quantity of interest, the heavy side of the expectation. So here, the heavy side is this dotted line here. The real value of the heavy side is 0, and my Monte Carlo approximation is going to lie with high probability anywhere within this Gaussian. And it's going to produce a value which is of the heavy side, which is again 0. So I'll be committing 0 errors. I'll not be committing any errors. The problem is when I have this red point here for a different risk factor, Y2, where the real value is of the heavy side is 0, but the Gaussian is either fat enough because of the variance of X given Y2, or because the number of samples is not high enough that the Gaussian is crossing the discontinuity. And then I have a certain probability that I'll end up with the wrong side, on the wrong side of the discontinuity. An O1 probability that I will end up on the wrong side of this continuity. And then I will be making an O1 error. I'll be making an error of exactly 1. So then I'm making either 0 errors for these, for points that are here, or an 1 error that for points that are here. So the variance will be the probability of ending up in this side here, which will be scaling by 1 over square root of NL, which is 1 over 2 to the power minus L, which is 2 to the power minus L over 2, so beta is half. Okay, so that's why my beta is half in this case. Alpha is 1 is just because errors cancel on both sides of this continuity. But again, we're not interested really in the case when beta is less than gamma. We would like to be beta greater than gamma, and then alpha doesn't matter. So what I'll be doing then is I'll be using more samples for these Y2 factors that are close to this continuity, or that whose Gaussian is crossing this continuity, such that the probability of ending up on the wrong side of the discontinuity is small or controlled. And the hope is that with this adaptive strategy, it's adaptive because for Y2 I'm using more samples, but for Y1 I'm using the same number of samples, or the minimum number of samples. I don't need to use more samples. So with this adaptive strategy, the hope is that I'll be getting beta equal 1, and which is equal to gamma, and then I'll be getting complexity which is almost epsilon power minus 2. Epsilon power minus 2 times log epsilon squared. Okay. So to do that, let's define this D. D is the distance between the real value, so going back here, So it's the distance between the real value and the discontinuity, and sigma is the width of the Gaussian, or the variance of x given y. So that's our definition of d and sigma squared. And it turns out the key quantity is this delta here, the delta quantity, which is d over sigma. And then I'm going to be choosing a number of samples which is between 2 to the power L and 4 to the power L. Okay? And this is the particular expression, but a picture is would be easier to understand. So here I'm plotting delta versus the number of samples that I'm picking. So when delta is large, meaning that my real quantity of interest is far away from the discontinuity, then I'm using the minimum number of samples, which is 2 to the power L. When delta is small, meaning my real quantity of interest is close to discontinuity, so my Gaussian is crossing the discontinuity, I'm using the maximum number of samples, 4 to the power L. And I'm only doing that when I'm close to the power L, to the power minus L, close to that discontinuity. And the reason is, if you integrate this, or if you calculate the area of this rectangle, it's 2 to the power L, because it's 4 to the power L times 2 to the power minus L, so it's 2 to the power L. And here it's 2 to the power L. And here you can actually calculate it and to see that it's also 2 to the power L when R is greater than 1. So it means that the number of samples on average, number of samples I'm using is 2 to the power L. But also, to remember that if I'm far from the discontinuity, I'm making 0 error. If I'm close to the discontinuity, I'm making an error. I'm making an error of order 1. So what's the probability of ending up here? It's 1 over square root of number of samples. So it's 1 over 4 to the power L. So it's 2 to the power minus L. And that's why my variance now is 2 to the power minus L. So my beta is 1. Assuming that this mid-region is not hurting me. This mid-region where I'm interpolating between the two. So that's for a particular level of L, for a particular level L equal to, and particular value of R. So this R determines how I'm interpolating between the maximum 4 to the power L and 2 to the power L. And if I increase the level, the minimum and the maximum increases. And if I decrease R, this mid-region is increasing. So I'm using more and more samples for values that are close to discontinuity. Okay, all the way to 1. I cannot use 1 because if I use 1, then this integrates to something that is more than 2 to the power L. So my number of samples will be too large. Okay.
Abdul, can Professor Shaikal ask you a question?
Yeah. I don't know why I don't have the
it's
chat.
Okay. I'll ask. How does this relate to Elphison's multi-level Monte Carlo with selective refinement? Sounds like the same strategy, just that in your case you've got a Monte Carlo inside and they have some finite elements inside.
I'm not sure.
When you're far away from the failure, they just basically use coarser grids, and when they're close, they use finer grids. It's pretty much the same strategy, no?
It could be. I'm not aware of.
We can talk it separate. Mm-hmm.
Yeah, I'm not aware of their work. I'll look into it. But yes, that's the idea. That when I'm close to the failure, I use more samples than when I'm far away from it. Okay, so the problem, of course, that in practice, d over sigma is not known because d is the exact distance from this continuity and sigma is the variance, which is even harder to compute. So a real adaptive algorithm will have to use Monte Carlo estimates for both d and sigma. Okay. So the algorithm we propose is to use, is for a given outer sample, is to use the minimum number of samples 2 to the power L, use that to estimate delta hat, to estimate delta, and then check if this particular number of samples 2 to the power L is enough in the sense of the previous, the optimal number of samples, if we assume that delta hat is exact. Okay, so delta hat gives us an estimate for the optimal number of samples, and then we check is our current number of samples enough or not. If not, we just double and recompute the estimate of delta hat, recompute the estimate of delta, and check again until we reach the maximum 4 to the power L. Okay, so this works in terms of algorithm numerically, but of course it's a different algorithm than what we analyzed if we assume that delta is exact. And the problem here is that if our delta estimates is bad in some sense, and we use too many samples consistently, then the cost is going to be large, larger than what we want. The cost is going to be larger than 2 to the power L. And if it's if we use too few samples, meaning that the delta is consistently larger than the real, our estimated delta is larger than the real delta, then the variance may be larger than what we want. So we need to analyze this, and the main idea of the analysis is to make sure that the probability of ending up with the wrong number of samples is small compared to the real number of, as we move away from the right number of samples that we would have got if we use the exact delta. Okay, so even though we might be using more samples or less samples than the optimal ones, the probability of ending up with too many samples or too few samples is small. And using that, we can arrive at this nice result on the adaptive algorithm. So this is on the algorithm itself, not on the idealized situation, where we assume that delta has a bounded density near 0. And this mainly means that not all my samples or not all my risk factors are ending up at the discontinuity or very close to discontinuity. There's some stretching. There's some, not stretching, but good coverage around the discontinuity. And that there's some boundedness of X for all possible risk factors. This can be relaxed to other P moments rather than the soup, but at some other costs. And then for any bounded moments here, I have my value R, which determines the interpolation between the maximum and the minimum. That changes the bound, because before I told you that R has to be between 1 and 2. Well, if I don't have enough sufficient regularity in terms of the bounded moments, then I need to tighten that bound a little bit. But in any case, if I use a value R that is between these two, then I get a number of samples that is 2 to the power L, while the variance is 2 to the power minus L. Okay, so just to introduce now the numerical example, in our case, we consider a portfolio of 1,000 heterogeneous options, heterogeneous in the sense that they have different nominal values and different computational methods. And we use 16 correlated assets. So 16 is just an example, but there's no dependence on the dimensionality of 16 or dependence on the 1,000, as we said. Both of these, our methods do not depend on these numbers. They do not degrade with these as these numbers increase, at least complexity-wise. And then the risk variable Y in our case is again the underlying assets at some short risk horizon. And this is important for the control variates that I'll be talking about later. And then the exact probability of large loss that we are computing is around 1%. So as I said, it's mildly rare. It's not too rare, the event of a large loss. Okay, so the losses can be computed by one of these three methods, and that's why I was saying that it's a different, just to model how in reality, in some cases, we might be able to compute losses exactly without any simulation. In some other cases, we might be able to solve the underlying SDE exactly and to simulate the solution exactly, but then have to compute the loss, have to compute the expectation. And in other cases, we have to approximate the simulation, approximately solve the SDE using some numerical time discretization method. And in here, we use the Milstein numerical scheme, and that's because we used the unbiased multi-level Monte Carlo for the inner expectation instead of just normal multi-level Monte Carlo when approximating the SDE. And this actually connects again to the previous talk. The nice thing about the unbiased multi-level Monte Carlo in this case is that our analysis, even though it was only for Monte Carlo, and in this case, we have some need for approximation for the SDE. This is because we use the unbiased multi-level Monte Carlo, our analysis just carries over. There's no need to do a special analysis for the unbiased multi-level Monte Carlo. And that's precisely because the unbiased multi-level Monte Carlo is set up as a Monte Carlo approximation. So in this case, the loss can be written as a difference between two functions, and this is important for the development of the control variates that I'll talk about here. So the payoff, the loss can be written as the payoff evaluated at the asset price at some maturity, TI, for given that the risk factors, the asset prices at time tau, again, the risk horizon, were exactly Y, minus the payoff at that maturity when we don't have that conditioning. So it's a different structure, and that allows us to use many control variates. So these are the control variates that we'll be using. First of all, there's a delta control variate. So as you see here, there's a difference, and we can use the delta Greek to linearly approximate the difference and use that to control variate to reduce the variability of xi. Then we can use the same Brownian path between tau and ti for both of these evaluations. So that reduces the variability. And finally, we can use an antithetic estimator between 0 and tau to reduce the variability of this part here and of xi in general. And then we use random subsampling with optimal probabilities that do not depend on the risk factor. They just depend on the relative weights estimates of the options. And we use an antithetic estimator, as I talked about before, for the multi-level Monte Carlo differences, which do not increase the rate of variance convergence, but they do decrease the variance a little bit by constant. So these are the methods that we look at. So the blue one here, first I'm plotting the variance versus the level, and you see that the blue full method is converging at the rate of 2 to the power minus L. The non-adaptive method, which is the red, is also converging at 2 to the power minus L, but this one I'm using 4 to the power L samples per risk factor, which will be clearer in the next plot. If I don't use the control variates, I pay in terms of variance. And if I don't use subsampling, I get actually less variance, but we will see the cost is higher if I don't use random subsampling. And finally, I'm also plotting the full method if I'm using some approximate simulation. So some 20% of the options require approximate simulation, and this will be the line. So I do pay a little bit in terms of variance. So this is the work now versus the level. And you see that if I don't use subsampling, I have a jump of 10 power minus 3 in terms of cost, which would be to be expected because I'm now sampling 10 power minus 3 options for every risk factor, while all the others are converging at 2 to the power L in the beginning and 4 to the power L in the beginning. But then using adaptive sampling, the asymptotic rate of these of the work is 2 to the power L, like would you expect. While when I use non-adaptive sampling, you see that it's 4 to the power L throughout. This is the red one here. And this translates to the work or to complexity, where you see all the adaptive methods are converging at rate epsilon power minus 2 log epsilon squared, like here, my full method, while the non-adaptive one is converging at the rate of epsilon power minus 5 over 2, because beta, again, is half in this case, while gamma is 1 and alpha is 1. Right, yeah, and this is just the runtime rather than the work estimate, which is consistent. Okay, so this was for the probability of large loss. What about other risk measures? So there's the value at risk, which is a different, it's the inverse of the probability of large loss. So here, instead of computing eta for a given lambda eta, I'm computing lambda eta for a given eta. And this can be solved by simple stochastic root finding algorithm because it's a one-dimensional problem. My only one dimension is the probability eta. And actually, by smartly refining my my forward problem approximation as I get closer and closer to the root eta, I can get the same complexity as for the forward problem, which is epsilon power minus 2 log epsilon squared. Conditional value at risk, on the other hand, which is the expected value of the loss given that the loss is greater than the var value. So for a given eta, can be written as a minimization where the minimizer is exactly the var value. So I only have to estimate the var value using an accuracy of order square root of epsilon, because it's a minimizer. And then I end up with I also have to estimate this expectation of a maximum. Okay. And in this case, the expectation of the maximum actually can be done much more efficiently because max is a smoother function. It's a Lipschitz function, unlike the Heaviside function. So that allows me to estimate it using multi-level Monte Carlo if I use the antithetic estimator with complexity epsilon power minus 2. So the overall complexity is epsilon power minus 2, assuming I also use random subsampling here as well. Right, so I promised other considerations. So the other considerations is that if, and this is a question that rightly many people ask me, what if can't I use surrogate models? So instead of estimating inner expectation using Monte Carlo, can't I just use a surrogate model to estimate it? And that's certainly true. So you estimate the inner expectation using some surrogate model and then estimate the full expectation using, for example, Monte Carlo. And that's possible. assuming that my function here is smooth enough, and also more importantly that y is not too high dimensional. If y is too high dimensional, circuit model, building the circuit model is going to be difficult. We can also use it as a control variable. And here, let me just plug in our work on weighted least squares polynomial approximation as a possible surrogate model to do this, if you so desire. And finally, if we saw that we have only one approximation parameter and we use unbiased multi-level Monte Carlo for it. If we have more than one approximation parameter for the inner expectation, then you might want to use a multi-index methodology, just like, for example, the talk by Joseph Dick in the PD application. So as Rob was asking or mentioning, that there's this other application where there's a PD approximation inside, and then you can use MLMC for that. You could see the talk by Joseph Dick, or you can, for a particular case of PD application, if you have other applications, then you can also refer to the original publication where we have the general complexity analysis under some variance bias and work assumptions. Okay, that should be the last slide. So risk estimation is a great new application. So we saw many techniques to achieve that performance: multi-level Monte Carlo, adaptive sampling, and subsampling, and also the very important control variates were used. So for this particular application, the control variates have a lot of benefit. If we have more complicated underlying assets, then we have to use multi-level Monte Carlo and MLMC, and that, or especially the unbiased version, so that we don't have to redo any analysis, and then that would lead to a nested multi-level Monte Carlo. And options, I didn't talk about this too much, but if we have heterogeneous work, then this can be easily done with a random subsampling, because now the optimal probabilities would depend on the work estimates as well as the second moment estimates. So these, all the results here are that I talked about are summarized in these two talks. And this first archive paper is the subsampling the unbiased multi-level Monte Carlo using the unbiased multi-level Monte Carlo for this particular application, and more details on the control variates. And this other publication in SIMUQ is on the more complete analysis with VAR and CVAR. And thank you very much.
Great. Thank you very much, Abdul. Very clear talk.